G'day. Today we're going to talk about the UCM. UCM is a Unitary Control Module. But before we get started, hit the subscribe button if you think you've got what it takes to last to the end of this video. So a UCM, let's dump it on the page. Let's have a look at him. Yep, it's big. It's really big. It's a Unitary Control Module. That's what it does. So let's set it up. Let's do this the easy way. Give it an enable. Drop that into the enable. Whoops, can't spell. Grab a variable. In this case it'll be temperature. Oops. Temperature. Oops. Be a set point. I'm not having much fun spelling today, am I? Set point. Let's grab another call this our fan status. Drop that in down here. I'll leave it out for now, just to use an example. Call this our chill water valve. Call this our hot water valve. And call this our fan. La, 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 la. Here's the fan. Cool out. Heat out. Okay. So, in the last minute and a half, we've just programmed up an AHU. Pretty simple, right? That's the whole point of it. It's a Unitary Control Module. It does everything. There's, well, everything practical. Okay. So currently, there is no enable, which is why the loop isn't processing. So let's give it an enable. Turn him on. It'll update in his 10-second execution period, which is this here. And it tells you that there's no fan status. So this Unitary Control Module in the unitary mode, in this unit control mode, requires a fan status to prove airflow before it will allow any heating or cooling. You can see the enable's on. The fan is also on here, but no cooling or heating's taking place because our set point's not right. Remembering these set points are in Celsius because, you know, that's where we live. So again, let that roll through its execution. Just drop this back to 5 for the sake of making it go faster. Okay, so again, fan, no cooling, no heating. So before we go any further, all of these E's in here, the whole point of that is to break up the property sheet into areas, I guess. This is the execution configuration. This is the loop mode. This is the after hours control. This is the enable up the top. These are the outputs. These are the input variables and set points. This is the deadband. This is the cooling loop configuration, the heating loop configuration, the fan status, the outside air offset enable, the unoccupied setback configuration, and our fire input as well as fan run hours. So the configuration has been broken up, and these EE things just help focus your eye on the area rather than squishing it all together and making it difficult to see because, you know, there's so much of it. So back to our loop, it's saying that there's no fan status. So let's connect our fan status up and minimize the block so we stop bouncing up and down. So fan status says stopped. So let's put our fan status on. Fan status now says running. Loop mode says cooling. And off we go. So every 5 seconds, our cooling output will update. Wait, we're cool only. Let's go dual band. So with the mode, we have a couple of, let's go through this section here. Obviously, the execution period is how often the block will execute with a minimum of 1 second. This elapsed timer tells you how long until the next execution, because why not? Also, if your execution's out to 60 seconds, it can get really distracting just staring at the thing waiting for the change. This offers good feedback for the engineer so that you don't have to anticipate when it's changing, you can actually see when it's going to. So the control mode, unit mode, or loop only. So in unit mode, you require the fan status before it will cool. In loop only mode, it doesn't require a fan status, it just uses the cooling and heating loops depending on how it's configured here. So the loop type, you can have cooling only, dual loop, which is heating and cooling, or heat only. So in dual loop, you can't cool and heat simultaneously, the block won't allow you to. So we'll leave it on dual loop for now, and you can see our heating output has bounced up to 17 based on our heating loop configuration, and every 5 seconds that heating output will start to wind on its integral. 52, and it will top out at 100 because that's the default for the heating max. You can set that back to 80, you can set the min up to 20, set it to 1000 if you want and rescale it later on. We haven't locked you into any kind of restrictions on the minimum. Pretty sure you can't make a negative though. Oh look, you can, how about that? So any number is valid and the loop will unwind until it gets to a negative value, and it will keep winding until it gets up to the maximum value. We'll go through these loop things a little bit later on, and we'll go through the deadband a little bit later on. Let's just look at the functionality of the block for now. So heat output's currently 100. We're running on a heating loop that is proportional and integral. So currently we have 0% effect from our proportional band, so we're riding the integral wave only. There is no proportional component directly applied to the output when this PB effect, both in heating and cooling, is at 0. I know a lot of other loops are fixed at 100, but you can ultimately have this at 25 or 100 or 200 or 0, and you can't go below 0. To help you tune the loop, sometimes we've found that you can get the integral value right, but 100% proportional action on the output just doesn't balance the loop out and end up sitting there for hours and hours dicking with the thing trying to get it to work. When all you really need to do is reduce or increase the impact of the proportional component. We never added derivative into this loop because the proportional value kind of acts as a derivative, and I've only ever found one instance in 35 years where we've needed derivative, and that was on a timber drying kiln. Again, it was well out of the ordinary, so we never applied it, and since that project, which was probably about 10 years ago now, we've developed this UCM and modified the proportional effect, which would probably have worked on the kiln anyway. So because it kind of acts as an anticipator, just like a derivative is supposed to. So All right, let's unwind our loop. Let's set it to, I don't know, 100, just to drive it into cooling, right? You can see the heating output will reduce, and it's not until it goes to 0 that the cooling effect can take over. It changes the cooling, winds up on the heating loop. Now the heating and cooling loop are completely separate. You can set one as proportional only. So let's set our heating as a PB only, just set the integral to 0. Now it's a proportional only loop. So let's also have a look at this PB effect. Let's set it at 100. So at 100 with a 23-degree set point, so let's talk about the proportional band. This isn't a gain, it's a proportional band. So it's 10 units. In this case, it's 10 degrees. It could be 10%, it could be 10 kilowatts, it could be 10 pascals. It's 10. It's 10 of whatever it is the variable is. So if we set, just to show you what that sort of means, let's set the cooling loop integral to 0. Let's put our set point down to 33. So proportional only, 10 degrees apart, we still have 100% output. If we drop this back to 32, we'll have 90% output when our loop executes, because it's 1/10 of 10. So currently our proportional component is 90. So there's only 10% left for its integral component. So if we let the integral ride, the integral is calculated, it's the error added over a period of time is how this loop is calculated. So what it will do is add this 90% over whatever time frame in minutes you've set this integral to be. So if we set that at 10, then it will take 10 minutes to add that 90 to the output. So it's calculated every 5 seconds. It will just keep adding 5 seconds of that 90, so that after 10 minutes, it will have added that whole 90% to the output. So if we drop this back to 28, it will still wind up. But you can see, because we've got 100% proportional effect on it, it's dropped back to 50. So the proportional component on the output is 50, and the integral component is 4.67, as shown in this integral total inside the property sheet. We put this here so you could see what the two different values are. The proportional you have to calculate yourself, but the integral component you can see. So if we change this proportional effect to 0, our output will drop to 5.92, or whatever it's going to go, 6.63. So you can see there's no direct proportional effect when you set this to 0. If we set this to 200, it will output 100%, because 200 of 5, 50 times 2 is 100. So output will be 100, and you can see once it hits 100, the integral component reverts back to 0. So as soon as you drop back, we drop this back to 27.5, the output will be 90 plus whatever the integral calculation is at that time, which is 0.38. Ooh, have we blown your mind yet? This is great, isn't it? Live for this stuff. All right. So obviously it works the same for heating. It's the same loop essentially, but you can configure two completely independent loops. So currently we've got the PB effect down here. Let's set this at 1.5 for heating. Let's drop this back to 100%. Let's let this wind up for a bit. Let's drop this down to 1 minute. Again, it helps get some integral component into the loop. Let's set this 0.1. There's no way to manually change this. You have to mess with the integral value to get the integral to wind up. So every 6 seconds. There we go. why that took so long. Yep, so 55 now. So then when you put this back to 1, it will just start creeping again. Let's drop our set point. We've already got our programs here, our settings 100. Right. Okay, let's put our temp back to set point. 23. So now we're at set point. Yeah, it wound up pretty quick, didn't it? Cooling output's 55. So obviously nothing's going to happen now because the temperature and set point are exactly the same. So this will keep executing. Our loop will stay in cooling because it's got a cooling output. And our loop just waits for a change. Let's drop this back to 22.5. And this will start to unwind the loop because we're now below set point. Inside our UCM, we have a deadband option. So obviously during the deadband is plus or minus set point. So if we set this to true, if we set this to 0.2, then our deadband is 23.2 to 22.8. So if our temperature increases to 22.79, sits in the deadband. Deadband true. Missed it. Went the wrong way. 22.81. There we go. Went the wrong side. And then the mode gives you deadband active. So even though it's not quite at set point, as part of your configuration in setting the loop up, you've decided that if it's within 0.2 degrees of set point, we don't really need to start micro adjusting the chill water valve to run it directly at 23 degrees because really, who can tell? It's so close to set point, it seems ridiculous to start micro changing or micro adjusting valves to try and maintain a exact set point. There are circumstances where you need to do this, but generally speaking, not. So that gives us our deadband option. So as the temperature increases, back to set point. Again, deadband. Yep, deadband still active. No winding of the loop, no managing. Everybody's happy. We can override this up to 23.19. Again, still within the 0.2 degree range. Managing itself, and then as we jump over to the 23.2, and it starts cooling again. And it will start modifying the output as per normal. So inside the deadband, it becomes a free zone where the loop doesn't make any changes because it's within a tolerance. Okay, so as part of the unitary control mode, if we lose our fan status, let's grab a one shot. I'm making what I want, but it'll have to do. Right, so if we change this, override off, as soon as we execute, it drives the chill water valve to 0 straight away. So, sorry, let's get rid of that one shot. Let's try something else. So if you want to manage this, grab our timer block, put it in the way, and then you can set an off delay if you wanted to, a 5-second off delay just in case your point's bouncing, or if you wanted to, you could also set an on delay, 15-second on delay, so it has to maintain the fan status for a constant period of 15 seconds before it will allow cooling. Let's put him back to true. Again, our timer is going to do its thing for 15 seconds. Let's just cancel that because that's just going to annoy me staring at that. Go through its thing, goes to true. It tells you here that there was no fan status. Now we're back into cooling mode. It resets the loop. It doesn't pick up where it left off. It resets the loop. And it starts cooling or heating again. So, okay. Goes through that. Let's just quickly go through the fire mode as well. I will grab that one shot. Grab your one shot. Drop it into the fire mode. Let's set it at 10 seconds. Okay, our fan's on, chill water valve's cooling, our hot water valve's not heating, our fan status is good, enable's good. All of a sudden, let's just rename this. All of a sudden we have a fire. I might extend this out to 30 seconds. All right, let's have a fire now instead. Fire. So the input says fire. The loop mode is fire. The fan has gone off. The chill water valve is set to 0. Everything is off. Chill water valve. The fan status says running, but this fire overrides or emergency stops this UCM, turning all of its outputs off. So once the fire, 10 seconds to go, once the fire signal resets, the UCM will start the fan, start its cooling or heating loop as per normal, and everything will resume. So you can manage this by putting a timer after it if you needed to sequence on your systems due to energy requirements rather than turning everything on at once. You could do that after this fire point if you wanted. Yeah, I guess after this fan, I suppose, I guess we don't need it with a hot water valve, but if we didn't have a hot water valve, let's say we had electric duct heaters instead. Let's call this our heating demand. In our timer, cut out in. Let's set our timer to an off delay of 120 seconds. Heat demand, let's grab a hysteresis. Grab our output, put that in here, hysteresis 5 and 55. Grab a second one, put it in at 45 to 95. Then we can put our Boolean override for heat 1 and 2. Hate that feature. And these become our heaters. Heater 2. Okay. Let's drop our temp. Oops, let's just have another look at that while we're looking at the heating loop. So the heating set point is different to the cooling set point. It has this set point offset. So we have our set point entry up here. And then because of where we live, we predominantly cool overheating. Where you live, it might be different. So in our cooling set point equals our set point in, our heating set point equals our set point in minus this offset. So if we set that to 1, our heating set point is now 2. And this is a proportional only control, so 22, our heaters will be at 100% output at 20.5 degrees. So if we set our temperature at 21, you get a 66% heating output, just like that, turning on one stage of heating. So then in fire mode, obviously this timer will still time out in fire mode. Need to be aware of that. This is outside the control of the UCM. You might want to put in, I know there are ways around it. You put in a Boolean switch in there, I guess, if you wanted to as well. Yeah, there's always a way around it. So this offers a run on. So if we turn our system off, override off, our fan runs on for an extra 2 minutes while all of our heaters go off. This allows for the heat to dissipate in the heaters. I'm not sure I believe it, but you know, I guess that's a story for another day. So there's our delay running for our fan. Our fan runs on for 2 minutes. Job done. So that's let's turn it back on again. Let's talk more about this proportional band. So at the heating demand for the heaters, what if we wanted the heaters to run past set point? We wanted the heaters to manage to be 25% or 25% at set point. While you're running a proportional only control, when the integral is set to 0, you have a heating bias. This will allow you to offset the range around the set point. So the heating bias, will make it 1 because it's too hard to, I guess at 1.5, let's leave it. Our heating bias at 25%. So now at 21, which is only 1 degree below, we've got 100% output on our heaters. 91.6% output on our heaters. So if we go back to set point, which is 22, because that's our heating set point, 22. At set point, waiting for our loop to expire. I got a deadband. Let's turn the deadband off. Right, we're in heating, and it's now 25% output at set point. I guess we put that deadband back on, because the deadband is for both heating and cooling. There's not a separate one, it works for both. So let's turn that back on. Let's make that 0.1. Let's drop this to 21.8, 33.8, 23. Oh, that didn't work. Wait. 22. Actions override 22. Again, while it's in there, it's probably not going to do anything because the deadband will be active at 0. Yep. So let's go 21.8. Wait for our loop to expire, and then we're at 33.8, which it will stay at through set point. And when it flows out the other side of set point at 22.2, it'll be 11.6. So the deadband will screw up the proportional band control, but you know, it's up to you how you want to control that. So I think that talks through most of the things. Actually, it doesn't talk through most of the things. Let's have a look at outside air offset. So some specifications call for energy management or energy control on degree days where the outside air temperature is outside the design conditions of the unit. So you're able to offset the set point based on that. So let's get a reset. Let's get a temperature. It didn't work as well as I wanted. Priority. Okay. Put that into our outside our offset. Let's turn that offset on. True. Okay, so our reset will be, let's call this, I don't know, 10 degrees Celsius to 15 degrees Celsius gives us minus 1.5 to 0. So currently at 0 degrees, we'll call this our OAT. So at 0 degrees outside air, we have a outside air offset of minus 1.5. So we can see our temperature is currently 23, but our cooling set point is now 21.5, and our heating set point is now 20.5. Effect all impacted by this rescale block here. So as our outside air temperature increases, if we went to 12.5 degree outside air, minus 7.5, then our cooling set point will be 22.5 and our heating set point will be 21.5. So you can see how this is impacting the set point without it actually adjusting the set point itself. The set point is still 23, but because we're outside of our design conditions, we're allowed to change the set points to manage our energy consumption of the plant. So it works the same way in a positive manner. So if we went 0 to 1.5 and made this, I don't know, 32 to 36 degrees Celsius, and override 36, outputs a positive 1.5, and now our cooling set point's 24.5, and our heating set point's 23.5. So it works both ways, and you can turn this on and off. This is linkable. You can turn this on and off based on times of the year. So now that it's disabled, see our cooling set point's back to 23, and our heating set point's back to 22. So, outside air offset, interesting tool if required as part of your system for managing energy consumption. So the other thing we have in here is setback control. So setback is like an unoccupied mode. What do you want to do in an unoccupied mode? It's varying things, let's say, not just one specific thing. We want to do many things. The first thing we're going to want is a schedule, an occupancy schedule. Let's call this our OCSCHED, so close. Occupancy schedule. We're going to want a setback value. So out occupied setback value. So we need to enable it. True. The occupancy comes from here. Our setback value comes from here. No, it doesn't have to come from here. We can just link it directly inside here. Our setback value might be 2 degrees. Excuse me, it might be 10 degrees. The other configurations we require are, do you want to run the fan in setback mode? Sometimes you do, sometimes you don't. You might want to stop the fan. You may require circulation in a lab space or something. You might want to make this 3 degrees overnight and 1.5 degrees during the day. This occupancy schedule here could be linked to the after hours block. So someone presses a button, they get 2 hours of occupancy. After the 2 hours, the system goes back to setback mode. You can choose to run the fan or not run the fan. Then we have the use heaters in setback. This is more for electronic heaters or electric heaters, not for boilers and things. If you've got a boiler, it's probably cold where you are. Electronic or electric duct heaters are quite inefficient in their energy consumption. So in an area, subtropics or tropics where we live, you might want to exclude heating. If it doesn't get cool enough to freeze things, you might want to exclude heating as part of your setback strategy, and that can be managed here. You may wish to include it during a calendar period and exclude it outside of a calendar period. So again, you can link varying things to this setback control to give you the desired outcome all in the one block. So in the last half hour or thereabouts, we've got an AHU program here that runs a setback strategy, outside air offset, fire control, heating and cooling control with split loop modes, one in proportional only and one as a PI control. Didn't really take that long, did it? It looks pretty neat, and that's pretty not really neat. I'd like to spend more time on that, but OCD gets in the way. And that's our Unitary Control Module. If you've lasted this long, congratulations. I didn't think it would go for this long, but it's a big block. It does many things, and I probably haven't really touched on everything, but it'll get you started. We may do another video on this. We'll see how we go. Cheers.